Hello there. So here we have vector, determinant, cross product, and dot product. We start with vectors over here, which I think we've done many times, but to be clear, basically this over here is the x direction, which is up to 10, which goes over here. And this over here is 9, which goes up here. Many ways to write that. There's more than one way to write it. It's your choice to write it this way or that way. I don't mind either way. Next, we have over here, same thing, another example, just going over here, but instead of doing the basic way, we have given polar coordinates a little bit of a reoccurrence and showing off what it kind of looks like to put polar coordinates. The polar coordinates allows us to simplify, but we need to, you can also go back to rectangle by this formula here. Anyways, next up would be more of this. I'm not doing more of that. It's just addition and subtraction. Basically, you add x. If you have two vectors or more, you add x with the x, y with the y. Um, really, not really that hard to understand if you knew it, but here's one example. What's happening here is that you get the x over here, and that x from the force over here goes to where was this one? This is the 90 newtons one. So over here, cosine. Over here, you see a negative because there's a going the opposite direction. As I said, uh, vectors care about direction. So over here, we have cosine 45, and spawn for the y direction. You just add it all up to get it. Um, so far, and there's some other law, cosine law, sine, if you want to use that, because technically vectors are just size if you think about it. And yeah, I mean, I'm oversimplifying, but then you kind of make sense over here. Over here, vector one, we get the magnitude of this one to get 10.344, which is fine. And you get the magnitude on the bottom with the vector on top over here. And that's how you get a unit vector. Huzzah! To showcase this a little bit more, I have showed the decimals. I know it looks a little bit goofy with that one, but yeah, I didn't want to change it because then I had to retype everything on decimals, and I did not feel like doing it. And it doesn't look as goofy as it previously was. So I would think it's fine. Over here, we go to 3D determinants and 2D determinants. We start with 2D over here because 2D is more intuitive. We visualize over here. Why did I put what? I'm questioning my sanity here because I'm looking at this and saying, well, why don't we just delete that and just continue like this? Visualizing the 2D determinant, that's so much better. Anyways, over here we have a 2D determinant, and this 2D determinant, as you can see, is a vector of this one and this one. And then over here, you can see that vector clearly over here, A, B, and C, D over here. It doesn't matter the or I mean, it does kind of matter, but does I mean, just keep on going, and this is your kind of 2D determinant that you get, and that gets the total area over here. Basically, is what's happening. Do. Anyways, we move on now. You can see the sample problems there. We're just going to continue. 3D determinant is a similar thing. You just have to split it into three parts, basically. And in the end of the day, this equation over here is what you get. All times you use your arms to block off the other two and make it easier to see the three splitting. There's many ways to split it. The other version of determinant is the same as this determinant. It's just that the different way of hiding variables to make kind of like a superposition thing. Well, it's not really superposition, but you get what I mean. Um, Dot products are next. Over here we have basically is a scalar. If you do this, it's just a summation of individual parts, like this summation with this summation. But the addition of a vector over here, you can get this this over here, which I forgot what it's called. I believe this is called a line. Yes, this is called a line that would parallel to the original B vector. So you just get this new A part, which is going to be parallel to B. Anyways, this is important because it kind of shows you what dot product does if you do a two vector dot product. You can do a matrix of vector dot product, but that usually requires tensors, and it's easier to do with index notation after that. But that's far above the scope of this class. No, no, sorry, the scope of this section. Yeah, anyways. So next up, let's explain what does dot product mean. So by itself, it just means the magnitude of this without direction. So it's basically um this scalar field like this that you don't really know where it's going to be pointed to. But with this direction, with this vector direction in v square, you are essentially giving it a direction this way. That's all that's happening. So it's a good thing that this is here. But yeah, but without that unit vector, it basically turns into just basically a what should I explain it? It basically is what it says. It's just a scalar. Anyway, let's move on because I keep on talking about this and we're not actually doing anything productive, I don't think. We have some properties of it. Obviously, a dot product, you can find the angle between, as you can see that theta. And then you have some property like the two same dot product is just v square magnitude no matter what. That's pretty cool. And we know a matrix version of it with vectors, but in all honesty, I don't really like this because a dot product can be more than just a two vector dot product. But in the case of this section that you don't know that yet, is good enough, I think. So that's why I made this textbook like this. Anyways, we move on to here where we have a dot product, which is a summation of different things, which is pretty cool because I think index notation should be taught when you teach dot products because it makes things easier later on. Anyway, we do some basic questions. I don't really think I need to explain this much because it's just numerical. The thing is, once you know how to do it with variables, there's no point to go back to numerical and do like 300 different questions. So I leave it like that. Anyways, we do the same thing with a cross product, but basically it's a determinant. So it's actually, let me go down here. Over here, you can see A cross B dot C is the determinant. So you just get rid of the dot C, and then you just leave the cross product basically. But in the reality, the cross product definition is like this. So as you can see, in the end of the day, you do the same thing as determining get this function over here, but that's really hard to memorize. So we have multiple ways of actually figuring out where the perpendicular portion of A cross B is. And then one is the right-hand rule. So you point the fingers and bring it in. As you can see, I made this. It's kind of a little bright because I was next to a bright window when I was doing it. Anyway, it doesn't really matter. It worked out at the end. And then we have some example questions again. The more, there's properties here too, and you can get angles from this by doing a reverse, by doing this thing. But in reality, the most important part is to prove again, because again, once you know how to do one of these, you pretty much get all of them. So there's no really reason to go back and do like 100 different questions of it. Um, yeah, in my opinion, that's definitely my opinion. But um, here the cross product, dummy variables, and all the other stuff with the index notation. Quantum Livy, this rule and this rule is going to be used for a lot of proofs. Um, so just note basically that I'm going to call it epsilon because epsilon is easier for me to pronounce. HAK, if you rotate these around like this, an even, so basically if it goes like this, let me just draw a unit circle like this. Oh my god, my drawing is awful. But you can kind of see this rotation. If it goes like this, if it goes anywhere, it can go back and forth also. So because they're dummy, I mean they're variables basically. You can go around like this and you'll be fine. The thing you can't. Oh wait, am I wrong? Oh, no, I'm wrong. Sorry, I'm wrong. Yeah, I'm wrong. Going that direction. Is that direction correct? I think so. Yeah. Oh yeah. Actually, you can go both direction, but just have to go linearly. You can't switch. That's what I'm trying to say. Okay, that makes a lot more sense. What am I thinking? It can go both ways. Sorry, I was right the first time. It's been a long. It hasn't been long. I just forgot. What you can't do is switch the order, like switch this to and this around and change it around like that. It's better if I actually show it off. Actually over here you can kind of see what I mean. These over here are +1, they're all plus, but if you switched it like this, equals -1 basically. So what does that really mean? If you look over here, you kind of can get the idea of these index, but why don't we just do one of these questions to explain to you guys. So A cross B, we start A cross B. We can't do calculus with, which is a bummer. I'm using a map, so it's kind of painful to do this. I should be able to do it. Over here, you see the original right now. So we can say epsilon I j k and say AI and BI. And actually thinking about it, why don't we just put it over here and just show where that is. Over here, you see that? The same thing with the M's. I thought, oh, I should have used IMN. That's more common, I think, but I don't know why you choose IML. Um, Anyways, you bring in this property basically over here, identity, and then you use the fact that you can if this if you see you distribute property, right? And you see an I and an I, you can change this and put drag this M over here because it's a chronicle delta. And you can keep on doing it right there to finally get this right hand side. And basically, because of how what's the right word? No calculus is involved. These proofs become quite simply just doing all that. There's only a few that are interesting. For example, these last two. And what happened here is basically I switched these around, which means there's a negative version over here because this is +1 and this is -1. So there's a need another minus to make it +1 from our rules we set out, which allows us to have a negative omega cross V. But over here, we use a similar property, but why can't it not be true? Because this over here is impossible to have. Um, you can also use probably anti-symmetric and symmetric. Actually, you can't because these are the same. Just never mind. I mean, no, actually, you could because they're saying, yeah, okay, maybe it'll work. I need to do all the math and figure that out. But basically, that equals 0. Anyways, yeah, I also only basically use in dissertation for things like this because it becomes painful to use identity to figure out the identities without these index notation shortcuts. I can implore you to try. If you want to try, go ahead. I don't recommend it. Next over here, we have another special case of vectors, imaginary vectors. These are actually vectors in reality. Uh, these are special cases because of the eye, and basically, unlike anything else, there's a rotational aspect to them. Basically, I square root of -1 is basically 90 degrees if you look at it in the signal processing. So basically, it's a special type of changing the angle of something, pi divided by 2. Over here, we do some basic summation and multiplication just to show off that basically imaginary is basically follows algebra rules. It's nothing new, just follows algebra rules. It honestly does. It just has some special properties. And over here, we see over here that 2 cosine negative is all just showing imaginary and real and trying to substitute it getting, but it's not really that important, really. The more important stuff was this proof over here. These two underlying proofs are kingpins over here of a lot of things. Uh, yeah, it makes it easier. It actually would have allowed us to do some of the earlier proofs easier. I don't introduce this because you need to introduce imaginary to component to it. And why that works is basically think about the imaginary vector, and you can think about this over here as I, and then this can be a sine x and then a cosine x. You have to know cosine and sine before you can actually even use imaginary, and then you introduce measures. I didn't do it before because it's going to confuse everyone. Now, the first is the showcasing superposition. Basically, it's not superposition, but it's a pseudo one because you can see that addition can be multiplication with a bunch of these things processing and showing it off. It's not always true, but you can kind of see that superposition kind of work. Um, but it's not really position, to my definition at least. We keep on going down, and this is like for the big ass proof I made. But honestly, all you need to do is this is true. This you just have to memorize that. Um, this is painful to memorize, and you know the funny part is you don't have to do any of the last portions. You know why? Because you can just go into your graphing calculator, and it's smart enough to get the imaginary real part if you do arcs do this function. Um, so there's no point in actually doing the proof, but the proof is interesting. Why I'm trying to hide away the proof is because it's actually difficult to do, because you can easily get this portion easily, but later on when you do a lot of things over here, it becomes tricky. It took a while for me to actually understand it. In the end of the day, I just recommend you use a calculator at that point. Here's some questions over here. It's not really proof based. It's just do you know your it's just questions basically. Interesting enough. Oh, here's an interesting case where I for absolute value. Absolute value always gets rid of a direction, right? It's the same case for imaginary 2D real to imaginary vectors. Basically, it's getting rid of any of the imaginary because it's trying to get some no direction. Basically, it's trying to get again the magnitude. Which is kind of what happened over here. If you look around here, it happened. It's not really that big of a deal, but yeah, that's kind of cool, right? I think something's wrong here actually. Fix it. If it's wrong, we'll figure it out. I'll figure it out later. Anyways, hyperbolic function, you have sine h, cosine h. It's all getting rid of imaginary, basically. You're getting rid of imaginary, and I'm not gonna, and then here I not improve, I just, by inspection, I find this out by looking at the graph and find out sine h equals negative sine. It's basically even and odd. I figured that out to just practice and looking at it and so on and so on. Here's a bunch of proofs you can do. Not really a big deal. I'll say one thing over here. This one actually is a longer proof because there's a lot of algebra here, but I didn't want to do it because it's kind of I mean, you could do it, but basically get leaks to this and this. Why I don't want to do it is because it's like a pain in the ass, and there's no point to it because I've done it multiple times. Um, But anyways, so on, and then we have more interesting bit where we add in the real and imaginary again. This is when it becomes interesting like this because it gives you a certain equation that's a little bit more harder to get, and I was like, okay, that's an interesting proof. And then we keep on going over here, just a bunch of proofs here. You can actually look through it, but I think I explained. The only one I didn't explain it as detailed was these, which yeah, these two. Everything else, I'm pretty sure I laid it out. So if you just look at it and read through it, you should be able to figure it out. But if you're seeing some, I don't know if you want to because it's kind of painful, and you don't use hyperbolic functions until like calculus way later on with ODE. Even ODE, sometimes you don't do it. You just leave it in no, exponential form, which is easier to really understand. So why would you go to hyperbolic? Yeah, hyperbolic is optional sometimes. If you just want to leave it as x instead, and a lot of exponents basically jammed in there. Now we go to polar, basically rectangle. Basically, what you have to do is plug these two equations into the equations, basically, except for these two where we do physically do arctan for each of them. But it kind of makes sense. It's just basically we did this before in other sections. I just That's why I just did two and moved on. Um, basically you plug in R cosine and R cosine into their respective like variables. Is this important? I mean, it is. It very is. But the thing is, I mean, it's important to know, but it's quite easy to do afterwards. I'm not sure if I should. I wasn't sure if I should do a lot of questions on it, but at the end of the day, I did. So there's a bunch of like questions over here on it. But in reality, it's the same thing over and over and over and over again. You can kind of look at it. I made sure to make it detailed so you can actually look at every step, basically. I don't think there's a single one that doesn't have steps already that is introduced and explained. So all of them are very easy to understand if you just look at it and just read line by line. Over here is the more interesting part when we say zero polar equation because we have r equals sine theta plus 0.1. Basically use arc sine, but here's the interesting part because this is what you use in Fourier's series sometimes. Basically you can do you get sine zero over here, but how to get sine zero? Basically n pi. N pi, if you think about it, it's like going to a unit circle every time that happens it hits it, so you can simplify it to just this. I could have just done this, but this is more interesting because this is important for later when you do signal systems. Same thing over here, same system, same power. And then we do parabola over here, which is a little bit more interesting, but again, I haven't used this version. I use the other version a lot more because of space mechanics, but this one is basically I don't know why I learned this in Trig. I should have learned this in somewhere else, but I learned this in Trig instead. So I'm putting it here, but I'm not sure if it belongs in here. But there's a directrix here, over here, going down over here. And basically this is A, this is A. And then we keep on doing that for a while. I do a few more of those questions over here. And then we go to polar equations, and I instantly get the elliptic equation over here and then get it down to this form. But this form is bulky. As you can see, this is bulky. And if it's off center, guess what? It becomes even more bulky. What this tells me is that it's good when it's somehow either crossing zero or going around the zero, showcasing that it's very reliant on the zero, because as soon as you try to get a vector outwards and make a function out like that, it becomes a little bit harder for me to do anything. Not to say it's impossible, but yeah. Uh, so in this case, we use a simpler version where we use this format over here, where we move a focal point, move the whole entire ellipse inwards, so we can actually loop that to 0 point over here to maximize the power of polar, is what we're doing. And basically, these are the equations that define it. So you can kind of see what I mean. Simplified, but understandable now, where it's going at. We have a directrix here. We have this is a parabola. We have this is hyperbola, and so on and so on. But it's very much more understandable and digestible to a common person now. So it can be very evident what's going on over here. You can keep on seeing it over here, um basically. And I purposely leave these sketches because I said sketches, I didn't say graph it, because it's very hard to graph these. So even if you wanted to, you probably only can get sketches by hand. In the end of the day, I think that's the best you can get. And then we do matrix multiplication, and that's important for space mechanics. This is all for space mechanics over here. And a few other stuff, but most the only thing I know mostly about that is space mechanics. I mean, there's also that one thing I forgot what it's called, but what that wasn't there some electromagnetism weird shenanigans that works with that? Um, I don't remember. Something like that. Whatever. And we have a matrix over here. Uh, um, I think this is not the first time we have introduced matrices as like multiple times, but in reality, the further I realize I go to math, the further I realize a matrix is kind of like the quote unquote one of the core math cores, basically. AI probably is changing that, but yeah. I don't know how to say about AI, but matrix is very important for computing. So, very big, excuse me, a big section of once again, uh computer science. Very big computer science. But you can keep on, and maybe even physics, and actually probably everywhere, because it's important for me too with state space and everything. Anyways, you can see how we multiply. I think our my general like imagery can is very evident here. So these two equals that one, these two equal this one, and so on and so forth. These two, I believe, equal this one, and these two equal this one. Now, is that obvious? I mean, I thought it was very clear, but if they're not, please tell me and how I could improve this. I so far continue to do some of those questions and some, but after you do one of them, I don't think there's a point to do more than one of these questions where you have a 3 by 3. So I'm not going to explain more of that. And then, actually, maybe I mean, here's another way to do it, but this is a computer way. Basically, a computer does it for you usually. So you just have to type in a matrix with a -1, square root -1 in MATLAB, and it instantly gets everything. Or something like I think it's invert INV parentheses A or something like that, if I remember correctly. And then you get this, and we finally get into calculus. You're finally there, and basically, the trig basically explains a little bit of calculus, the limit portion and the definition, if I remember correctly. So in the end of trig, you start calculus. You start a little bit in calculus. So let me just explain a little bit calculus. The definition of limit. This is an informal definition. This is basically going into existent territory. Does it exist? Does it cross and exist over here? That's basically it. And I believe that's all that was explained in the trig, so that's all I'm going to say right now. And over here, the slope is the rate of change, and that is what derivatives are, is what you need to, everyone needs to know that. And then here is such an interesting, over here is operators. Operators are important because if you do a function and then put an operator, it's like adding multiplication or something like that to it. So these are operators. That means that to make it linear, this function is only you just have to make sure that f is appeared once on the top or f doesn't appear again. I'll say linear later on, but I think I'm done here, so I'm gonna stop here because I believe this is the end of trig. This is a crash course, I guess, in this sense, and you can look at my textbook more if you want. But I have explained all of trig in a short time. I'm gonna stop.